Hi everyone, I'm Hu Shishuai from Northwestern Polytechnical University. Today I will present our work on label propagation for carotid visual segmentation and atherosclerosis diagnosis. This work is done by me and Liao Zehui under the guidance of Professor Xia Yong. In this challenge, our goal is to segment the visual from 3D MR image and diagnose the atherosclerotic lesions. Based on our observation, we found that this task is challenging mainly due to two reasons. First, we can only access limited and discontinuous well-annotated slices, as shown in this page. As a result, it is hard for us to train a robust segmentation model. Second, the appearance of healthy and diseased arteries is heterogeneous. We show one case in this page. It shows that the brightness of the normal visual and the diseased visual is different. Thus, the segmentation performance of the trained model might be worse on carotid plaques. To address the issue caused by the heterogeneous visuals, we formulated the carotid visual segmentation and atherosclerosis diagnosis task as a 3D segmentation task that segments lumen, normal visual, and diseased visual from 3D MR scans simultaneously. Since the 3D structures of lumen, normal visual, and even diseased visual should be preserved well, because the normal visual and the diseased visual are defined as two different classes, the issue caused by their heterogeneity can be relieved. To address the issue caused by limited and discontinuous annotated slices, we interpolated 2D discontinuous annotations to 3D visuals. Besides, since more than half of the slices on the MR scan are not labeled, we use a simple but effective semi-supervised self-training strategy to propagate the labels to the whole MR scan, and use the propagated labels to retrain the 3D segmentation model. This is the workflow of the proposed label propagation framework. It is mainly composed of label interpolation, model training, label propagation, and model retraining. First, we use the nearest neighbor interpolation to convert the 2D discontinuous labels to 3D visuals. Then, we use NUNet as a backbone to perform 3D segmentation using the MR scans and the corresponding interpolated labels. Since the original left carotid visual and the right carotid visual were labeled respectively, the labeled indices of them might be different, leading to some missing labels at the start or the end of the left or the right visuals. Therefore, we split the whole MR scan into single-side MR scans to train the model model A. With the trained model A, we can generate pseudo labels for the whole MR scans. However, the generated pseudo labels might not be accurate enough. Therefore, we use the interpolated labels to correct the pseudo labels. Using the propagated labels, we retrain a 3D NUNet model, model B, with the whole MR scans. Since more data can be used for training, the robustness of model B can be further improved. During inference, we only use model B to perform inference in a sliding window manner on the given test image. Then, we can get lumen, normal visuals, and diseased visuals, of which the latter two are regarded as visuals for the segmentation task. For the diagnosis task, we split the whole MR scan into single-side MR scans and classified the single-side MR slice into normal or diseased by judging whether the MR slice contains diseased visuals. We have evaluated our framework on the Cosmos Challenge dataset. This is the implementation details of our framework. We use depth similarity coefficient to evaluate the segmentation performance of our method on the training dataset, and use a metric provided by the Cosmos Challenge to evaluate the performance on the testing dataset. We show the segmentation performance of 2D model, segment model A and segment model B using full fault cross-validation on the training dataset. It reveals that 3D segmentation models are superior to 2D models on visual segmentation. Also, it shows that segment model B improves the segmentation accuracy a lot than segment model A, confirming the effectiveness of the label propagation strategy. On the testing dataset, our method achieved a score of 83.14 and got the first place on the online evaluation leaderboard. That is all of our presentation. Thanks for your attention.
Hi everyone, I'm Jong Kim, and I came second place in the quantitative evaluation of the challenge. Let me explain the method I used. First, carotid vessel segmentation. Carotid vessel segmentation was performed using 3D method. Data preprocessing is required for 3D segmentation. First, we create a segmentation label from the given control point. We train 3D NNUNet in 2 steps. In the first step, NNUNet is trained with the preprocessed data. Because the 2 images are not ground truths, in the second step, NNUNet is trained again using ground truths and prediction from the first step. Then we convert the second step's prediction results back to the control point and enter them into the cascade file. In classification for atherosclerosis diagnosis, we create a 4-channel images using segmentation results to train CNM models and predict carotid disease. In preprocessing, first we crop the image in half, then create 2 types of preprocessing images. One is stack of annotated slice, the other is linear interpolation of the empty space between 2 annotated slices. We simply drew a straight line after sorting the control points of 2 slices at an angle with the center point. The model segments the area into 3 parts: background, lumen, and outer wall. Segmentation is performed through 2 steps. In the first step, NNUNet is trained using preprocessed data. In the second step, first step prediction and ground truth are used to train the NNUNet. The weight of the ground truth is higher than first step prediction, and the gradient flows only to the annotated slice when trained ground truth. After that, we perform 5-fold cross-validation and ensemble the results. Let me explain the classification method. First, crop the patch image using the segmentation center point. Then, using segmentation results, we create a 4-channel image by applying masking to the patch image. For training the CNN models, use the 4-channel image as input. The 4-channel image consists of 3 masking images and 1 patch image. The 3 masking images consist of a vessel area, a lumen area, and an outer area. The masking image was created using the result of segmentation. Let me explain the implementation details. The patch size is 48 by 48 and 4 channels. Flip, rotation, and elastic deformation were employed for data augmentation. I use exception with a batch size 256 and a drawback rate of 2.3. We train for 200 epochs with the LMW optimizer. Label smoothing was used, then 5-fold cross-validation and ensemble were used. Thank you for listening.
Hi, I'm Inyena, a master's student under the supervision of Professor Hyunjin Park from the Medical Imaging Processing Lab at Sungkyunkwan University. I would like to present my work in Cosmos 2022. To perform vessel wall segmentation and atherosclerosis diagnosis, we construct the method of a three-step pipeline. First, we localize the center point and segment the lumen and outer wall using the extracted polar patch. And finally, atherosclerosis is diagnosed based on the polar patch masked by the segmentation result. We use the unit to locate the center points of the arteries. The model receives 3-channel input of 3 consecutive axial slice images and returns a center point proximity map. The model is trained using dice and mean-squared error loss. Dice loss is calculated after applying the sigmoid function to the proximity map. The center point is obtained by extracting the peak from the proximity map, and post-processing is performed to refine the center point. Clustering is performed between candidate center points with an error distance of 10 pixels or less. Then clusters are merged through up and down tracking, starting with the cluster with the most points. Up tracking travels from neck to the head, while down tracking travels in the opposite direction. Up tracking works like the flowchart on the screen. Down tracking performs the same by reversing only the relationship between the start point and the end point. Polar conversion is used to simplify the segmentation task. A polar patch is extracted using the center point of the previous step. The CNN-based model receives the 3-channel polar patches and returns the lumen LADI and outer LADI from the center point. The model is trained using the polar intersection of union laws. The vessel contour can be obtained by converting from polar coordinates to Cartesian coordinates using LADI and center point. The model for diagnosis of atherosclerosis is composed of the squeeze and excitation network and long short-term memory modules. The input X is per-channel image and is obtained by applying masking to the polar patch. This model performs binary classification and is trained with binary cross entropy. To generalize the segmentation and classification models, various augmentations are performed on the polar patch. First, the center point of the polar patch is shifted in the x-axis and y-axis directions. This serves to increase the robustness of the localization model. Second, the polar patch rotation is performed. This is to change the starting angle and direction when extracting the polar patch. Finally, the image is downsampled by a factor of 2, followed by upsampling to the same size to simulate interpolation noise. These steps encourage the models to be generalizable, accounting for varying degrees of image quality. This is the validation and final performance of the pipeline proposed in this study. We ranked 3rd place in the final leaderboards. In this study, vessel wall segmentation and diagnosis of atherosclerosis are performed through the proposed 3-step pipeline. In this process, polar conversion and problem-specific augmentation are applied. As a result, robust results were obtained despite the limitation of a small training dataset and varying image qualities from different slices. Thank you for listening. If you have any questions, please feel free to email me at the address on the last page.
Hello everyone, this is Team MRJ for 222 Cosmos Challenge. Corroded vessel wall segmentation has some unique challenges compared to usual medical segmentation tasks. First, the shape of lumen and vessel controls can be commonly shape of concentric, smooth, and closed circles for small vessels. However, the shape of axisotorotic vessel lumen varies from oval, eccentric, and small circle, and the crescent shape. Lumen shape largely depends on the block distribution. Second, in terms of the smooth and the pipe-like nature of carotid artery, the lumen and wall segmentation should have smooth enough shape. For normal vessels, the lumen and the vessel wall have a control of convex closed curves. Another challenge is only the internal arteries was delineated in this challenge. Thus, some of the fault results, like the area of external carotid arteries, may occur. The choices of algorithm was considered for these reasons. In practice, lumen and wall regions were decided by radiologists in context analysis from raw image. This should be a consideration when choosing algorithm. After initial segmentation, some morphological constraints should be added. They remove the unnecessary parts of the results. Last, algorithm should be easy to implement and tune. The first part of the proposed algorithm pipeline is data preparation. The input images were crossly divided into left and right parts of by means of hubbing the imaging in the left-right direction, which divided in DICOM meta info. Next, given the menu mask was delineated just in limited actual slices of the image, a linear interpolation was conducted to generate a rough, complete lumen and vessel wall mask for upcoming model training. Then, some meta info such as image spacing, metric size, and the intensity distribution were recorded for the upcoming segmentation workflow. The second part of the proposed algorithm pipeline is segmentation. A 3D cascade in a unit framework was implemented to get vessel position and 3D segmentation. A cascaded 3D unit network architecture was trained in 5-fold cross-validation. The optimal configuration was automatically set in a unit framework procedure. Finally, the best 1 or 2 model were assembled according to the cross-validation performances. The 3D segmentation output was labeled as segmentation 1. Next, a 2D in a unit framework was implemented to get fine 2D segmentations. The 2D in a unit framework was very similar with 3D version in training strategy and configuration optimization. The 2D segmentation output was labeled as segmentation 2. Some morphological operations were utilized. For the left and right vessel was separately processed. There was only one vessel in each image, thus the largest component was kept. Shape amelioration was consist of mass center analysis, which means the distance between lumen center and the vessel wall center should be smaller than a user-defined threshold. Bifurcation slice was detected as a sudden decline of the vessel area. For last and next 3 slices from the bifurcation slice, 2D fine segmentation was set as final segmentation. For the other distal slices, the intersection of segmentation 1 and 2 was considered as synthetic segmentation output. The third part of the proposed algorithm pipeline is axisotorosis diagnosis. Taking segmentation results the input, some key vessel wall perspectives was calculated lumen area, wall area, as absolute measurement of the carotid arteries and should have approximate values for normal vessels. Normalized wall index was calculated and provided as an imaging indicator to distinguish plaque and quantifying plaque burden. Distance between lumen and the vessel center was considered as measurement of the eccentricity of lumen, which was the obvious phenomenon in carotid arteriosclerosis. By means of above characteristics, a classification model was implemented to determine whether the slice is atherosclerotic. The better performed model was chosen. Some evaluations should be added to further test the model robustness. Our successive plan gives 2 examples of model sensitivity analysis. First is to test the model robustness to noise. Second, some displacements mimic meandering situations were added to vessel center to test the model performance in terms of the disturbance of the imaging continuity. Given sensitivity analysis should be conducted in the test dataset, this step will be finished after the announcements to the details of the test dataset. Some limitations are obvious in our methodology. Here's general segmentation framework was utilized with some specific post-segment processing, not a dedicated model. Without individualized optimization, the choice may reduce the performance of models regarding of a segmentation task of a specific part of vessel. Another problem is the interpolation of the given mask. This may violate smoothness of vessel nature in saturation, especially interpolation from 2D scattered slices to 3D volume. Another problem is the interpolation of the given mask. This violates the smoothness of vessel nature in a select direction. Especially interpolations from 2D slices to 3D volume. Potential improvements are proposed to improve the model performance, including adding some convex and close control constraints in forward step of the model, such as some dedicated loss functions constructed from polar coordinates. Additionally, change to more realistic mask interpolation methods will make better training standard and may further improve the model performances. For the final observation, we ranked fourth among all teams. The detailed results of the test set have not been published by the organizers, thus we calculated specific results of the proposed model on the validation site. The metrics contain the similarity coefficient and so on. And the results of the proposed model are marked with yellow rainbows. That similarity coefficient reached a good level of 0.834. The volume differences normalized wall index differences and the horizontal distance of lumen. Our model achieved the best performance in validation phases. It also performs well on other quantitative measurements. Thank you.
Hello everyone, thanks for inviting me. It's a pleasure to be here. I have been invited as a result of being selected one of the top 10 teams in the Cosmos 2022 challenge. As you already know, the objective of this challenge is to segment the outline of the wall and the lumen into MRI sections, both the internal and the common carotid artery, and also to detect if there are atherosclerotic lesions in the area. When I started trying to solve this challenge, my first try was to use the full image as an input. But as you can see, it has a lot of black pixels that are not adding a lot of information. So the second try was to crop the center of the image and extract the relevant patch in the middle. Later I tried, because in the second approach you still have a very big image, and you are trying to segment a small crop in one of the sides of it. So I tried to extract from the second version, the second image you can see here on the screen, extract the small patch of the region of interest we are looking for of the carotid artery. And later, in the fourth and final version, I added, as you can see here in the RGB channel, both the previous, current, and next slice to add some 3D information into the model. Each of the iterations, from the first to the fourth model, were a clear improvement in the dice coefficient. This is the architecture of the proposed solution. You can see that it's clearly divided into both the high and the low level components. And the model starts with the raw image. We are extracting the relevant patch in the raw image and making it go through the segmentation network. We obtain the first segmentation. This segmentation is able to locate perfectly where the carotid artery is, but we have a problem here. It's not able to detect the finer details, for example, the lesions and also the bifurcation in some cases. So that's why we make a crop. We add 5 pixels on each side, and we make that crop go through the second segmentation network. It's the same architecture, but we are training it differently, and we get the finer resolution segmentation from this second network. For the classification of the lesions, we use the crop segmentation, and we are able to achieve a very good accuracy from it. The model and the training parameters are as follows. We are using Adam as the optimizer with a learning rate of 0.001. We are reducing the learning rate on plateau, early stopping, and the batch size that we can fit in our GPUs was for data augmentation. We are using translations, rotations, and random noise. For the high-level model, the rotations were limited to small angles, but For the low-level models, we use full slips both in the horizontal and vertical position. And lastly, before presenting the final results, we were using test time augmentation. We performed all these augmentations in the image in order to get a lot of different results and average all the predictions, and that improved our score. The training of the high-level model was able to converge in between 6 and 8 hours, and as you can see, it's able to locate the area of interest really fast, but it has some difficulties on adjusting it perfectly. But talking about the low-level model, in just a couple of seconds, in a couple of epochs, we are able to get very good predictions and get super fine results on even these difficult cases. Talking about the results, you can see a mosaic here with all the frames of my validation set. In most of the cases where there is no bifurcation or any kind of lesion, you can see that the prediction fits almost perfectly to the ground truth. Green pixels here are true positives, red pixels are false negatives, and blue ones are false positives. The model has some difficulties into detecting pixels with lesions, or here in the bifurcation, for example, is selecting the interior curve of the artery instead of the exterior one. For the next steps, I would like to try an automatic detection of the bifurcation and train a different model to perform that task. Also add information from more slices, not just the previous and next ones, and train with more data, maybe even generate some samples with GANs. Also, we are here working with, we're trying to predict circles, and I think that if we perform some kind of transformation, because we have this anatomical prior, right? We know that the shape that we're trying to predict, and if we convert it to some kind of curve, maybe it's going to be an easier problem. Right now we are not performing any kind of post-processing, and sometimes our predictions are not a perfect circle, and that has an impact on the score in this challenge. That was it. I hope you find it interesting, and thank you for your time.